Okay, everybody. Good morning.
Good morning, Professor.
Okay. Okay, more people are coming. So okay, more people are joining. So here we go. How do we do remove, increase, remove? Here. Assignment. Let's see here what's going on. Assignment. Let's see. Assignment. I don't want assignment. Let's try something else here. Okay, I'm uploading a new version of the syllabus right now. Version number 2. Let's see how I can. Module. Module. How are you gonna do that? Publish. Assignment. Assignment. No. Page file. Let's see. Select file you want to associate with this module. Huh. Okay, so maybe I create a new module. Syllabus. Let's try this one here. Okay, check version number 2 of the syllabus, please, and see if you can see it. Let more students are coming online here. Let's see, admit all. Let me show what I did here, and I want to start sharing my screen. Let me see, where can I find the recorded? I didn't upload yet, Daniel. I'm gonna upload it. Those files are very big and their quality is not very good either. My experience with Zoom is that the video quality of the files is not very good, but I will upload it. It's what you, yeah, let me see here, check for, let me put it here, you know. Let's see, recordings, last recordings. And look for my YouTube channel. My YouTube channel. For Claudio Egalon, right? Claudio Egalon. Let me see if I can get the exact link here. And I'm going to start sharing the screen. Let me check.
Professor?
Yeah.
Would it be possible if you could, on your syllabus, if you could post when the tests are going to be?
Yeah, I'm gonna do that. I'm gonna do that. I didn't get to this point yet, but I'll let you know. Okay, I'll let you know.
Professor.
It's gonna be next week. Okay, it's gonna be sometime next week, and you know, we're still at the beginning here. I'm taking my time so everybody can adjust, and then I'll let you know when it's gonna be next week. Okay, admit all more. Let's see your channel. Okay, videos. Okay, so here you go. I'm gonna share the screen here. I have a bunch of videos there in my YouTube channel. Here you go. And I am going to get this link here. YouTube channel. That's the link. So let me save that. And what's new here? What's new in the syllabus? My office hours. Office hours is gonna be 2 to 3 p.m. after the class meeting. Okay, and we are meeting from 8 to 2 p.m. right? And then office hours from 2 to 3 p.m. The link is the same that you're using. The Zoom link is the same for the office hours. And the class recording, I'm going to upload to my YouTube channel in this link here. Let me, oh, what else is new here? I start working on the syllabus, on the schedule, okay? I didn't do this column yet, but I will get that to you. I'm expecting to have our first lab here next, you know, tomorrow, not today, but tomorrow, lab 1. We have a total of 19 meetings. You can see we have a total of 19 meetings. Okay, and we have a total of 9 labs. So we are going to, you know, what is the schedule for the lab? We are going to do some lecture instead, half of it, right? So you can fill up. We're going to have a holiday on July 4th. Let me share with you also my spreadsheet. Here you go. I was working on the schedule. You know, here you go. Here's the schedule. Is that what it's supposed to? Let me see here. No, this one that I want. This one that I want. Okay, the hourly load. Lecture is 3 hours and a half. Labs is 2 hours and a half per day. Total is 6 hours plus 1 hour of office hours. Okay, so here's the load, lab plus lecture at the end of the summer is going to be a total of 114 hours that we are going to meet. Plus the office hours. If you sum the office hours, you know, end up with 133 hours that I'm available with you folks to meet you all. And like I said, I should have to finish this part here. When it's gonna be the lab, whenever which labs we're gonna do, when it's gonna be the exams and so on. Let me update the syllabus that I posted there. Go back to the canvas. Where's my canvas? Looks like I gotta go back to the canvas. Okay, here you go. That's the one. So I'm going to delete this one. See here. How do I delete that? Remove, right? Yeah. Hit place. I want to make sure you can download it. Can you please make sure you can download that? I have the older syllabus here in this module, and now it's version number 2. Drop syllabus in here. You mean in the chat box? I don't think I can do it, but let me try. I just let me see. Let me see if it works. Yeah, see, it doesn't allow me to do that. Let me try it again. Let's see here. Let's see. Drop Google. Yeah, it doesn't let me drop in the chat. Okay. Sometimes it allows me to do that. Sometimes it doesn't. I do not know why. Yeah, check. Yeah. Not everybody has access to Canvas, right? Let me post this document in my Google Drive as well. Okay. And I'll give you a new link. You're gonna have lots of links here. Some of the students that are in the
Professor,
yeah.
I was wondering, on the days that we don't have lab, what are we doing during the lab time, or do we still have lab time?
We're going to do lecture. We're going to do the lecture. We're going to lecture, solve problems, things like that.
Okay.
And Google Drive, view, admit all. Okay. Now let's go to the Google Drive. Summer group folder, and I'm going to create a new folder here. Share folder. Now here we go. And that's going to be, so this folder here is for whoever doesn't have access to Canvas yet. Anyone with the link, you won't be able to edit, just to have access to those files. And you go share, copy link. And now everybody will be able to have another link. And I'm gonna put my syllabus there. Okay. Good, the syllabus is there. And there's one more document that I want to put there. It is the Wiley Plus setup. Here you go. How to set up your Wiley Plus account there. I already have homework number 1 there in Wiley Plus. So if you want to start practicing the problems.
Professor,
Yeah.
about Wiley Plus, I have my account, but I cannot see any homework.
Really? Let's see. I did that yesterday. Anybody else is having a problem with Wiley plus? Let me go there to Wiley plus. Let me stop sharing. Plus login. Let's see if I can. Physics 39 current. That's the one. Okay, see home. Ah, that's because I didn't publish. Okay. Okay, shows in there. Now you should be able to see it, right? Let me see edit. I'm going to.
Yes, I can see it now, Professor.
Okay, good. Thank you. Chapter 15, oscillations. Okay, so now we're in good shape here. Thank you for letting me know. We have 32 students so far. Okay, and
Professor, do you know
Yeah.
when you're gonna make that homework due?
oh yeah, good point, right? Let me see what I put it here. I believe I put it, yeah, I put a due date in there, but I cannot see that. Let me see. Edit. I remember putting a due date yesterday. Maybe I put it a week or something like that. Does it show there in your more options? Maybe share to commons, master path. Huh. Here. Animated illustration. Edit assignment settings. Let's see here. Edit assignment settings. Oh, you didn't save it, huh? It's strange. Huh. Yeah, it's supposed to have a. Yeah, I did that yesterday. For some reason, you didn't take the successfully added. Okay, so let's see. Let's put the due date next week. Today is the 14th. Let's put on the 23rd. Available. Huh. Can I put it for today? Yeah. Assigned to 11/3/92. Why do I have 2 here? Everyone else. This is a good assignment. Assigned to everyone else. Okay, I don't think I need this one. Let's see. Okay, check if you have the due date there now, please. Yeah, now we have it. Huh. I did that yesterday. For some reason, it didn't show up. Maybe I forgot to save it. So 23rd. Okay. Notes and 3. That's my. Those are my notes, right? Chapter 1 oscillation. Okay, so what we started doing last time. Here you go. Here's my PowerPoint slide presentation. We started looking into the pendulum. Okay, we're doing the free body diagram of the pendulum, the forces that are applied to the bob. The string is assumed to have a very low mass, a negligible mass. So, but we're going to continue studying this problem later on, okay? This one is a little bit more complicated. So what we're going to do next, and we're going to come back to this one, to the simple pendulum. Not only going to start talking about the simple pendulum, we're going to come back to the simple pendulum, but we're going to also review another type of pendulum, that is the physical pendulum. As I mentioned before, there is a practical, here's the physical pendulum. There's a practical application for the pendulum, and that's for as a element for a timekeeping device. In addition to those two pendulums, the simple pendulum and the physical pendulum, we also have another type of device that can be used for timekeeping that uses a spring. You have studied the spring before, right? Hooke's law. The spring applies a force in a mass that obeys Hooke's law. And consider a system just like this one here. A mass attached to a spring. This position in the horizontal direction. Instead of y, let's put x, right? Instead of y, let's put x. The mass is initially at its position of equilibrium. By position of equilibrium, what do I mean? I mean that the force that the spring applies to the mass is 0. Okay? So if we take the mass out of equilibrium, like something like that, take the mass out of the position of equilibrium, right? Well, what am I doing here? I am applying a force with my own hands to this mass that's connected to the spring. Okay? That's an external force. When I apply an external force here, the mass get out of equilibrium, and we end up having another force on another direction, which is the force, not this one, and I'm going to put it in a different color as well, red, so it's easy. This force here is going to be the force of the spring, the force that the spring applies to the mass. And I'm going to put that in red color, so you know that the red, I'm going to put a little bit lower here so it's not superimposed to the spring. You got? Right? So now the mass is no longer in the position of equilibrium, and the moment that I release, well, here you go. The moment that I make this external force equal to 0, the moment I release the mass, the spring is going to apply. The mass is going to be subjected to an acceleration to the right, to the left. Okay, here you go. I'm going to put here an acceleration, which is going to be dependent, according to Newton's law, is going to be m divided by the external force, right? Does anybody remember what's the force of the spring here? That the spring is applying to the mass? I'm going to put here x. I don't want to use y. Y is usually used in the vertical direction, right? Let's put it x. Another one. Good. Okay. The moment I release the mass, we have this force here of the spring applying to the being applied to the mass, and this mass is going to move back and forth. Here you go. The spring is going to can go ahead and put more. Here you go. Put more slides here, right? Let me get here you go, another slide. Go back to the position of equilibrium. Here you go. One more. I'll get this one as well. That's what the nice thing about PowerPoint, right? And throughout the whole motion, I'm gonna even include the vector force, right? Here you go. Here you go. That's the first frame of the slide. And I'm going to take advantage of all this thing that already came up with. Here you go. At this point, we're going to have another acceleration, but the acceleration is going to be less, and the force is going to be less as well. Okay. But do you remember what is the equation for the force that the spring applies?
Is it mg equal to negative kx?
That's you know, keep in mind, mg is the weight, right? Mg is the weight, right? Do you agree with me?
Yes.
Yeah. Okay. So the force that the spring applies is kx. Yeah, it is kx, but mg is the weight. Okay. So let's see. Here's gonna be okay. Yeah. So it's gonna be kx in this case. Let me put x here. Let me see. I have another one here. X. The force here is going to be at this point is going to be 0. And we represent a 0 force with a dot. I'm not going to put the acceleration is going to be 0 as well at this point because the force is 0. Okay. As the spring passed the position of equilibrium, what's going to happen to the force? The force is going to invert the direction, right? Here you go. The spring is going to invert, the force of the spring is going to invert the direction, and so will the acceleration as well. Can you picture that? Here you go. One more. Here you go, maximum amplitude. And maximum acceleration as well. And we're going to write down those equations. Here you go. Spring. Then we can play the movie again. Here you go. One more slide. Here you go. One more frame of my movie. Here you go. The force is going to decrease in magnitude. And so that the acceleration. In this type of motion, the acceleration is not uniform, right? The acceleration varies as time goes by. The mass is going to pass through the position of equilibrium, just like we had before. Here you go. I will take advantage of this other slide. Here you go. And the whole motion is repeated again, but now, let's see, the force is going to be inverted. This one, I'm going to use this one. Inverted, here you go. The direction of the force and the direction of the acceleration. Here you go. Okay, one more. Right, and I'm gonna get the other acceleration vector, this one right in here. Here you go. And then we can play the movie. Oh. This one here. Let's play the movie now. Here you go. We made the. Here is the mass initially at the position of equilibrium. I take the mass from the position of equilibrium by applying an external force. Here you go. And then we release the mass from this position. Let's say this position here, I'm going to call X naught. That's what's missing from this drawing. Get used at making drawings like that. They're so simple drawings, you know, and yet it tells you so many things. Allows you to visualize the situation, the physical situation. And that old story, right? A picture is worth 1,000 words. Here you go, X naught. So here you go. Position of equilibrium, take out of the position of equilibrium, I'm applying my force to the right. I can even, you know, go ahead and put here, you know, this force is going to be a little bit less than the external force that I'm applying with my hand, because the mass is still moving to the right. Right? And now I release. External force becomes 0. In the next slide, I'm going to specifically write down that the external force is equal to 0. I cut down here to 0. And now the mass starts moving. Here you go, back and forth. Here you go, position of equilibrium, overshoots the position of equilibrium. The force that the spring applies to the mass is start increasing, but in the other direction. And the acceleration too, here you go. Now the mass is moving to the right, pass to the position of equilibrium again. The force that it springs applied to the mass is 0. And by the way, I'm assuming that there is no friction here. Frictional forces are negligible, okay? That's what I'm assuming here. Let's put that here. Frictional forces are negligible. Let's say we're doing that. This type of experiment, we're doing that at the arcade in that air table. Frictional forces are negligible. Here you go. Here you go. That's the picture that you have to have in your mind. You know, the mass oscillating about the position of equilibrium. Okay, let's solve this problem. You know, just like one of our students told us, right? The force that the spring applies to the mass is going to be kx. The magnitude of the force is going to be kx. You learned that in mechanics. That's Hooke's law. We call that Hooke's law. So let's get our notes. Not this one. I want another one here. See, this one must be this one. Yeah, that's the one. Today is the 14th. Okay, here we go. Force that a spring applies to a mass. Equation. Here you go. Strictly speaking, you know, the force of the spring, and I'm gonna put a vector there, like that. idea. I don't want the vector all the way down there. Let's see here. No, I'm gonna do differently. Here you go. Vector. You know, I recommend you to learn that stuff here in. Okay, here you go. The keystrokes to draw through those equations. So what's the equation for the force of the spring? The vectorial, right? The vectorial equation is going to be minus kx and x hat. X hat. That's the vectorial equation for the force. Okay. Don't forget this negative, right? The force is opposite to the displacement from the origin. And then if we want, the idea here is find the equation of motion of a mass attached to a spring of constant k, right? That's the idea here. So should treat that as though it's an example. Find the equation of motion of a mass attached to a spring of a mass m attached to a spring of constant k. Ooh. The amplitude of motion is x. The amplitude of motion is x naught. Okay, so given all that stuff, so let's go back there. Go find the equation of motion of mass attached to spring of constant k. The amplitude of motion is x naught. So going back here, amplitude of motion. What's the amplitude of motion? Is the position x naught. That's the amplitude of motion, x naught. And what else you gotta say? You have to say that assume that frictional forces are negligible. And what else I have to tell you? Negligible example. Find the equation of motion of a mass m attached to a spring constant. You know, the amplitude of motion is x naught, and the mass moves in the horizontal direction. Okay, so that's very important. Remember, this type of motion here is in the horizontal direction. Because the motion in the horizontal direction, you know, you do not have that mg equal to kx, okay? You do not have the mg equal to kx. Remember that student that mentioned about the mg equal to kx, okay? If you're going to account for all forces, right, do a free body diagram. Here you go, we have the spring here. We have also to show the other forces that are acting in the mass, right? We do have the mg here, but this mg force is being canceled out by the normal. Okay, here's the free body diagram. It's being canceled out by the normal that we have right here. Here you go, normal. Okay. So because the mg is canceling by the normal, you know, this mg is not going to show up in our equation in the Newton's second law that is going to give us the equation of motion. That what we're going to do. So here you go. That's the equation of that's the net force applied to the spring. I'm going to write that down here. Here you go. Net force applied to the spring. Now applied to the mass, right? Net force equal to force that the spring applies. If I'm going to be, you know, if I want to be strict about this whole thing, we can even put all the forces that are being applied to the mass, right? But like I said, this term here ends up being equal to 0. Okay, net force we're going to apply Newton's second law. What you have here, no, you're going to have a 0 according to our free body diagram. I'm going to even change, you go, net, instead of force that is being applied, well, net force applied to the mass. I can go to the next line here, and then you go, net force is going to be the force of the spring plus mg plus n, right? Net force becomes just the force of the spring, and then I can finally work out this. And then you can come back and say, no, force that the spring along, force that the spring along applies to the mass, You go. And that's going to be, here you go. I'm going to copy all the stuff. Here you go. And now I'm doing a step-by-step derivation here for you. What's the next step? You know, apply Newton's law, Newton's second law to find the what? The equation of motion. That's how we find the equation of motion of an object. We first find the net force applied to it, and then we use Newton's second law. Here you go. Net force equal to what? What's Newton's second law? Mass times acceleration. Here you go. Mass times acceleration. And then mass times acceleration, we can here write that as being what? d2x. Yeah, here go d2x, right? dt2. And I don't need the x anymore. Let's go. I want to make it look better. This equation, go like that. Here you go, in the x-hat direction. And now I'm going to simplify this equation. What do I mean by, okay, and I get this differential equation. The x-hat that you have on the left side cancels out with the x-hat that you have on the right side. Okay, and take it out. I did something like that similar in physics 38. If you took my physics 38 course, you're going to remember that, something similar like that. One of those oscillating circuits, LC circuit. And now we have this mathematical challenge of solving the position X. Okay, how to, now we have, we have a differential equation in terms of X. If we solve this equation, we will be able to determine the equations of motion. Okay. Anybody knows how to solve this equation? Okay, so take a look at this equation. You know, I used to have a professor there in Brazil that he would tell us, you know, you look at the equation, you start talking to the equation, you know, and hope that the equation talks back to you, right? You go look at the equation. I don't like talking to equation. I don't see this the right way of expressing that. If you want to solve equation, talk to equation. Now you don't talk to an equation. You analyze the equation and then you use your experience to find out how to solve the equation. Okay. In this specific case, at this point in time, most of you should know already how to solve the equation, right? But let's see what this equation is telling us. In a way, let's see what the equation is talking to us, right? The equation is telling us the following. This equation is telling us the following. If you differentiate the function x twice, okay, comma, you are going to get the same function multiplied by a constant. Okay, that's what this equation is telling us. And I'm even gonna write this equation. Go divide by m, right? That's what this equation is telling us. I go ahead, differentiate an equation that I do not know. I'm going to make things simpler for you right now, and I'm going to tell you that you get the same function multiplied by a constant. Minus k divided by m is a constant. Okay? And now I'm going to ask you, what are the functions that you know that when you differentiate it twice, we get back the same function multiplied by a constant, right? That's the question that you have to ask yourself. What functions that we learn out there in differential calculus that you differentiate once, you get the same function, and then you differentiate twice, you still get the same function multiplied by a constant. You folks should know what this function is, right? Any volunteers there that you want to? Give some feedback? Go ahead, type there in the chat box so you can have some participation. Okay, I have anybody want to risk? Oh, yeah. Okay, Daniel. Daniel, give us an answer. Okay. Let's see. Thank you, Robert. Here you go. Okay, that's Daniel gave an answer, and Zach gave us another answer, right? Think about that, Daniel. Sine and cosines, they are solutions. You do get a sine or cosine back if you differentiate twice, right? But if you differentiate it only once, you do not get the sine or cosine back, right? If you differentiate a sine once, you get a cosine, right? If you differentiate only once, the cosine only once, you get the sine, right? But yes, Daniel, either sine or cosine is a solution for this second order differential equation. Yeah. But if you want to be more, genetic, if you want to be more genetic, let's see. What if this thing was just not the second order, but the x dt only, right? You'd get exponential. And the exponential also satisfies the second order derivative, okay? And then Daniel came with this, with a solution similar to Zach. Okay, yeah, so let's try. Let's see if it works, right? Let us try the following. Let us try the following solution. X, okay, here we go. X, I'm gonna put here a constant, exponential. I'm gonna put 80. Let's try the solution here and let's see if we get anything out of that. Okay, those are unknown constants so far, A naught and A. T is a variable, an independent variable. T is an independent variable, X is a dependent variable. Let's see if it works. We substitute that right here. Okay, we go ahead. Let's see, I'm gonna get this first derivative, dx dt. Dx dt. A naught exponential AT, and then you gotta multiply by A. That's my first derivative. The second derivative, oh, I don't need that, I already have it here. The second derivative is going to be A squared times A naught exponential AT, okay? Substitute that into this equation right in here. Okay, let's not forget to substitute that into the X as well. Here we go. Going back to our differential equation, right? I don't need that. We can start. Remember, I still do not know what A naught is. We won't be able to find A naught right now, but you're going to find out later on. Look what happens. The exponential on the left side cancels out with the exponential on the right side. And then look what we get. We get an A that's going to be a square root of a negative number, right? K and M are positive numbers, right? So if we take the square root of a negative number, we're gonna get the complex I times the square root of K over M. Okay, and here you go. We have this solution here. X is going to be A naught. Let me put another step here so you don't lose track of what we're doing here, right? It's going to be a complex exponential. Everybody has seen complex exponential before, right? From this simple analysis, we come to the conclusion that the X, the complex exponential, what's a complex exponential is all about? That's the Euler equation, right? Okay. A complex exponential is nothing but cosine okay. Okay, cosine plus I. That's what a complex exponential is all about. So that solution for cosine and sine is correct. And where it comes from? It comes from the solution of the exponential with a complex argument there at the top. Okay. Depending on the initial conditions, we might not have a sine or might not have a cosine, but they're always going to depend on the initial conditions, okay? So let's take a look at the initial condition, okay? Initial condition. Initial condition of our problem. What's the initial condition of our problem? X at t equal to 0, right? Remember the amplitude? X at t equal to 0. is equal to what? X naught, right? Equal to X naught. But you substitute 0 here as well. And you get what? From the initial condition, we find the value of A naught. We find the value of A naught. Okay. And let's continue here. X. What time is that? 8:55. X, see here. We can put X naught right here. Okay. But what's the other initial condition that we have? The other initial condition that we have is that dx dt at time equal to 0. Let's see how I'm going to do that. I'm going to do like that. It's going to be 0 as well. It's equal to the initial velocity, by the way. That's equal to 0. Okay, let's see that. Okay, so also remember, right? In order to have something like that, you know, the solution, we can rewrite the solution in terms of sine and cosine right now, right? You already know that exponential is a complex argument, is a combination, linear combination of sines and cosines. So for this specific case, in order for the initial conditions to satisfy our problem, what we must have? We must have that the solution must be something like that. Okay? At time t equal to 0, cosine is going to be 1. X is going to be x naught. That's my first equation of motion. My second equation of motion is going to be in terms of the velocity, sine. Okay, and we must have a negative value right in here. At time t equal to 0, sine of this term is going to be 0 as well. And then the third equation of motion is going to be for the acceleration. Here we go. Acceleration is dx2 dt2. We get cosine here. Okay. Oh, wait a minute. I'm forgetting something here. I gotta put the argument as well on the outside, right? And I have to put this. I have to do the same for the acceleration. Here is going to be the velocity. Here is going to be the acceleration. Okay. So that's how we solve this problem for simple harmonic motion. That's what we call simple harmonic motion. This type of motion is called simple harmonic motion. What you have right in here is very similar to the components of the circular, uniform circular motion, by the way. You gotta know how to solve this problem, okay? And I spelled out how to do that here for you. We got the equations of motion for the case in which we have no friction. Don't forget, frictionless case. That's the frictionless case. It's 9 o'clock right now. Yeah, it's 9 o'clock right now. Let me take attendance. And any questions about that? Would you mind going back to the previous page? Just missed something. Okay, just tell me where to stop. Okay, so Sarina. There is? Okay, good. Let me shrink a little bit because I want to share this screen with another document. Can you see that? And that's the one I want. I'm gonna shrink it. Okay, that's fine. I put a picture of the thing. Okay, good. Okay, good. So I can fill it up. Fill it up. Here we go. Toby, are you there, Toby?
Yeah, I'm here.
Okay, good. Thank you. Now, Harun, are you there, Harun? No, Harun's not there. Musa, are you there, Musa? I don't see Musa either. Jumai? I don't see Jumai either. Let's see. Zachary is here, right? Zachary.
Yes, I'm
Blue?
here.
Okay, good. Thank you. Elena?
Hi, Professor.
Hi, how are you doing? Luis? Crystal? Luis Crystal? Let's see if Luis Crystal is here. I don't see Luis Crystal in there. Brian Spino? Good, thank you, Brian. Robert Faust? Good, thank you. Pedro Flores?
Here.
Good,
Here.
thank you. Lawrence Flores? I don't see Lawrence here. Okay. Daniel Freire?
Here.
Good. Amalia, Daniel, Freire is like a Portuguese name, right? Is that a Spanish name too, Daniel?
Yeah, it's both Portuguese.
Both Portuguese, both Portuguese and Spanish. Okay.
Yeah.
Okay. So your background is Spanish, I presume, right?
Correct.
Okay. Okay, thank you. Amalia Gale,
Here.
thank you. Tiffany Wang,
Here.
I can't hear you. Too low.
Here.
Okay, thank you. Tiffany. Olivia Kruger.
Here.
Okay, Daniel Yang. Thank you, Daniel. Anthony Lopez.
Here.
Shuk Lu.
Here.
Okay. Davey Maes.
Here.
Okay. Ryan McNeil. Thank you, Ryan. Gabriela Montes. Gabriela didn't show up. Huh? That's the second time she doesn't show up. Okay. Daniel Nwagbu.
Here.
David Nwagbu.
Here.
Good. Claire Ottinger.
Here.
Angela Padua. No, are you there, Angela? Let's see. I don't see Angela listed here. Okay. This is the second time Angela doesn't come. Maria Haju. Maria. Don't know Maria here. And Jennifer Ramirez. Okay, Noah Raymond.
Here.
Thank you. George Risk. Thank you. Shafi.
Here.
Thank you. Natalie Santiago. Natalie was here. Yeah, I see her listed here.
I said here, Professor.
Okay, good. Thank you. Nathan Silva. Good. Darnice Simon. I see listed here. Is Darnice there? Okay, I'm gonna put a star. I see in the list, but I don't hear. Kadi Sobi. Kadi, not listed here either. Second time doesn't come. Aidan Tadeo. Tadeo, let's see, not listed either. Okay, so far, Sandra Valencia. Sandra there. Nope, I don't see Sandra. Let's see who's coming. Okay, Harun. Kenny Villagomez.
Yeah, I'm here, Professor.
Okay, thank you. Robert Wall. Robert, are you there? Let's see. Robert. Nope, no Robert Wall. Another student. Nolan Williams, are you there, Nolan?
Here.
Okay. Mengshu. Thank you, Meng. And the issues that are in the waiting list. So, Kieki, so, are you there? I thought I saw her here. Nope, I don't see it. Yeah. Olivia Song.
Here.
Okay, thank you. Sarina Lobana. Okay. And Alexis Nigret. Are you there, Alexis?
Here.
Okay, thank you. Let's see, Musa and let's see, we have 34 here. Okay, Harun, are you there?
Yeah.
Okay, and Musa.
Yes.
All right. So let's see how many we have. I see 33 students, but I see only a total of 32. Who was not called? Was not called. Let's see. Ki, so are you there? Ki, PSO? No. Let's see. Jumai, are you there? No. Luis Cristo? No. Let's see. Lawrence Flores. I don't see Lawrence listed either. Let's see. Gabriela Montes. Maybe someone is logged in two different devices, maybe. Angela May. No. Maria Raju. No. Oh yeah, yes, Darnis. Okay, that's the one. Okay, are you there, Darnis? I just kept just okay. That's the one here. Okay, so let's 9:08 right now. Let's have our break. Break till we're gonna do like 15 minutes, right? 9:23 a.m. Okay, 15 minutes. And what I'm going to do, I'm gonna pause the recording so you don't get all those 15 minutes recorded, right? That we're not doing anything. And please remind me to turn back the recording when we come back, okay? I'm gonna pause and record, okay? Thank you. Okay, so we're gonna get the period of oscillation now, based on the equation that we found. In order to get the period of oscillation, the position of time t equal to 0 must be equal to the position of time t equal to the period capital T. And then we have to solve for this equation that you see right in here. Okay, so here we go. We go ahead and substitute for t equal to 0 and substitute for t equal to capital T. Okay. In the next step, X naught cancel X naught. All right. Cosine of 0 is 1. And we have, this equation in which this argument must satisfy this condition. Cosine must be equal to 1. So we go ahead and you look at the, let me see if I have the, I have to do the trigonometric circle, right? For the cosine. Here you go. And I'm gonna get this x-axis here. I'm gonna view the grid lines so I can have a better reference. Let's see, 1, 2, 3, 4, like that. Yeah, 1, 2, 3, 4, 1, 2, 3, 4. That's good. That's the x-axis. You need to visualize, right? X-axis, y-axis, the cosine. How is the cosine here? The cosine is going to be 1 here at this spot, right? It's going to be 0 at the top and bottom. Trigonometric circle for the cosine. It's going to be -1 here. At theta equal to 0, the cosine is going to be 1. And at theta equal to 2 pi, cosine is going to be 1 again, right? So going back to our case, so the argument here that we see, you know, this guy that we have right here must be equal to 2 pi n, okay? And 2 pi n, and by the way, for n equal to 1, 2, 3, blah, 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 right? Well, actually, we want for n equal to 1 only, right? Because it's the shortest period that we want. So here go for the shortest period. Here go for the shortest value of t, n must be equal to 1, and consequently, what we must have here is 2 pi, and we solve for t. This square root becomes m over k. Okay. That's the period of oscillation. That's how long it takes for the mass to complete a full circle, a full cycle. Okay, and by the way, this term that you see right in here, we give it a name. The term, okay, is given a name. Name is called the angular frequency. versus frequency. It's not the same thing. Angular frequency and frequency, they're not exactly the same thing. They're different, okay? What is the definition of frequency? Definition of frequency. Definition of frequency is, how many oscillations you have in a single second. In a single second. That's the definition of frequency. What's the definition of period? Definition of period. How long it takes? How long it takes for a single oscillation. That's the definition of period as well. Here is how long it takes to complete a full oscillation. Here is how many oscillations you have in a single second. So there is a very close relationship between frequency and period. One is the inverse of the other. One, here you go, is the inverse of the other, okay? Which ends up doing, let's see, 1 divided by that, right? Put everything between parentheses here. Okay, here you go. And we can simplify this relation equal K over M. Equal. That's how we relate one with the other. Don't forget, what else do we have here? Okay, don't forget that this guy here, right, is the angular frequency. The angular frequency, which, by the way, we represent by the Greek letter omega. Okay, so what we end up having here is something like that. The relationship between frequency and angular frequency is something like that. I can write down omega in terms of the frequency, the angular frequency in terms of the frequency, invert that. Okay, so those are the equations we have. Let's make a summary. Summary. Okay, you go omega. Omega is going to be K over square root of K over M. Period is going to be something like that. And the frequency is going to be the inverse of the period, which is something like that. Okay? Or another way to write the frequency in terms of the angular frequency is omega over 2 pi. Okay. That's what we have here. Any questions about that? Okay, so here got the solution in my notes. Okay, here you go. Energy, let's talk. But before we move forward here, let me just remind you, right, of the links that you have so far for this course. A little break here, links for the course so far. One, Zoom link for the class meetings and the office hours. That's what we have. 1. A link for my Google Drive with syllabus and other documents. Okay, these are also shared. In my Canvas page, in the Canvas page of the course. What else? What else? We have link for my YouTube page. Okay. Did I put that in the syllabus? Let's see here. Oh yeah, right in here. Class recording. Class recording, right? Link for Wiley Plus. Man, you have a bunch of links here, right? Link for Wiley Plus. Oh, and the link for your group folder for the lab. So we have those 5 links, right? It's also in my Google Drive. Google Drive. I've been using my Google Drive for a long time. It works pretty well. Okay. Save that. Okay, and let's go here. Here you go. So now we're going to talk about energy considerations in simple harmonic motion. Okay. So the first thing that you have to know is the kinetic and potential energy, right? Well, let's remind energy considerations. Energy considerations in simple harmonic motion, SHM. Okay, so we have to know is the kinetic energy. M V square. Okay, and you have to know about the potential energy. Potential energy of a spring. Remember what that is? Half kx squared. Half kx squared. Well, recall that x is, you go, that's what x is all about in simple harmonic motion. And we also calculate that the velocity is something like that. Don't forget the negative sign. Here you go. So let's go ahead and substitute that for kinetic energy and the potential energy. Right? Here you go. That's going to be like that. And here you go. Potential energy. And let's see, I'm going to need that as well. That's going to be cosine here. There is no negative sign, right? Because it's just the x. Here you go. Side by side. Then that's a little bit spaced, a little space here. And we're gonna get here, we're gonna take this guy, the negative sign cancels out when we square it. The square root of k of m cancels out, and the sign becomes squared. That's how the kinetic energy changes as time goes by. Can I do better than that? Yes, I can do better than that. I can cancel out m with m. And what about here? Okay, here we're gonna get x naught squared cosine squared, easier than the other one. And here you go. That's how the kinetic energy and the potential energy varies as time goes by. What about the total energy? What about the total energy? Okay, the total energy is going to be kinetic plus potential energy. Plus potential energy. Go. That's the kinetic energy, and that's the potential energy. Because we have common terms here, right? And this common term involves the sum of the sines and cosines. It's multiply, and look what we have. We have conservation of energy as well, because sine squared plus cosine squared is 1, right? That's what the total energy in simple harmonic motion is all about. It's equal to a constant. Total energy in this case doesn't vary in time because there are no frictional forces in there and no external forces adding energy. There's no frictional forces subtracting energy and no friction and no external forces adding energy to the system. That's total energy, total mechanical energy. And go. The derivation is all here. Total mechanical energy, that's the total mechanical energy. And here we have a comparison between simple harmonic motion and uniform circular motion. Simple harmonic motion is a one-dimensional type of motion. Uniform circular motion is two-dimensional type of motion. Notice that the argument, in both cases, we have a cosine here. And the arguments, it's just a slightly different parameters, right? But the functional relation is the same. Because this is a two-dimensional motion, we are going to have an equation for y position as well. The velocity is going to be something like that. Look here at the relation. Negative, negative, right? What you have right here has units of velocity, which coincides with the initial velocity of the particle undergoing uniform circular motion. Sine and sine, right? Same thing here for acceleration. Amplitude. Amplitude for this case is x naught. Amplitude for uniform circular motion is going to be a. Okay, and by the way, a is the radius of the circle, okay? A is the radius of the circle, if you recall. Maximum speed, square root of km times x naught. Maximum speed is v naught. Maximum acceleration is something like that, okay? And that's what we have for simple harmonic motion. And now we can start talking about the simple pendulum. So let's go down here with, here you go. That's what we have, simple harmonic motion. And I'm going to copy this one. Let's copy those two here. Here you go. Well, there's a reason why I started dealing with the spring, okay, before the pendulum. Historically, that was what happened, right? First people discovered that the pendulum undergoes this oscillatory motion, and then later on they developed the springs. It's easier to build a pendulum than, practically speaking, it's easier to build a pendulum than to build something like that. But mathematically speaking, it's easier to solve this problem than to solve this other one. That's why I started solving mathematically this problem here. And now we're going to do this one right here for the pendulum. The simple pendulum. So what you have to do, you have to come up with the force diagram, free body diagram. I am going to upload the notes to Canvas. Yes, Daniel. Okay, and also I'm going to put that in my Google Drive. Also going to put that in my Google Drive. Okay. So let's here you go. It's let's take that into account, the forces. Now, why mathematically this problem is a little bit more difficult? Well, that's because it's a two-dimensional problem. Okay. Yes, that's right. I'm going to work on an actual problem. Remember, all those solutions that I'm making here, they are actual problems. Okay. Okay, Sha. So, for instance, this the case of simple harmonic motion. This is, you can consider that as an actual problem. Okay. And I'm solving like in a generic fashion. This thing that I did today, right now, this is, you can consider that an actual problem, like an example, just like a, formulated here example, right? Find the equation of motion of the mass and so on.
Okay.
So this is an actual problem, and so is the pendulum as well. It's going to be, we can think of them as being actual problems. More than that, you have to put numbers in there to see how it works, right? Numerically.
Yes, Professor.
Okay. So let's talk about the simple pendulum problem. Simple pendulum problem. Difference between one and the other. So this one is a 2D problem, two-dimensional problem, whereas the simple harmonic motion is a 1D problem. Okay, that's why we start studying this one first. But the procedure is very similar. The procedure is very similar. We use Newton's second law of motion, just like we did before. I'm going to copy and paste what I had there before. The steps, here you go, net force. No, not this one. We want this one here. It's not going to be the force of the spring. It's going to be something else. Okay, so here you go. That net force is going to be what? It's going to be the weight plus the tension. There is no other force in there. Here you go. I can take this one out, right? And because this is a two-dimensional problem, we must have MA there on the right side or, the two in a vectorial sense, right? We take the second derivative of the position with respect to time. That's the type of equation that we have to solve. Here goes simple pendulum. Let's write it down, example, right? Find the equation of motion of the simple pendulum. Simple pendulum. And then length L, mass with a bob of mass M attached to a string of length L. That's how you should look at this type of problem. This is a 2D problem. Let's see what I put there. Did I put lowercase m or uppercase m? I'll put uppercase m. Let's put uppercase here too. Length L, that's good. Neglect frictional forces, neglect frictional forces, and the mass of the string. Neglect both of them. One more time. Let's see here. So here go mg and tension, right? You go. Okay, there is you can either solve this problem in the XY plane, or you can use a different coordinate system, okay? The nice thing about this problem is that it can be reduced to a one-dimensional problem. That's the nice thing about, okay, even though this problem is a 2D problem in the Cartesian coordinate system, right? XY plane. Okay, we can reduce it to a 1D problem if we choose a proper coordinate system. That's why we teach different coordinate systems. In one coordinate system might be easier to solve a problem than in another. And that's what happens for this specific problem of the simple pendulum. If, let's go ahead. I'm gonna go here. Like I said, I could solve this problem using the XY coordinate system. Yeah, I could do that. But then I will have to keep track of each coordinate X and each coordinate Y. But what if, go here. What if instead of the Cartesian coordinate system, I use a different one? I want to displace a little bit, okay? I use a polar coordinate system. What about that? In the polar coordinate system, I'm going to need the following. I'm going to put it here, red. Yeah, better, right? That's the radial coordinate. Okay, so instead of x, now I have the radial coordinate. And which other coordinate we have in the polar coordinate system? Okay, which other coordinate? We have the radial coordinates, and then which other coordinate do we have in the polar coordinate system? Describing the motion of this particle in the polar coordinate system. What would that? What would be the other coordinate here in this case? Huh? I'm asking you folks. While you think about that, let's move this guy around here. Yeah, the angular position, right? And I can, let's see, this one right here. I can completely define the position of my bob by its radial distance from, let's say, this origin. Let's put the origin right in here. The drawing is becoming too busy now, right? Here goes 0. Origin of my coordinate system. Here you go. Here's the and let's see if I can get my arrow there. Yeah, here you go. And here's the angle with respect to the vertical of this of the problem. Here you go. And this one I'm going to call it the theta coordinate. Well, the advantage of this system is that my radial coordinate is constant. My radial coordinate, that's the advantage of the system, is constant all the time. It's equal to the length of the string. I'm assuming that the string doesn't stretch, doesn't compress, and always remains, even though it can be bent, right? It always stays the same length. Okay? That's the advantage of this coordinate system. And now I can go, let's see, let me do something else here too. I'm gonna draw the pen. Let's see if I can do that. Well, it's a little bit difficult to do that. But anyway, you know, this mass is oscillating back and forth like that. Okay. So we have only those two forces, the tension and the weight applied to this guy. Okay. Because the radial distance is constant, what does it mean? It means that the net force along the radial directions is also constant. Okay. So let's write that down here in the notes. So for this reason, we will coordinate system for this problem. This proper coordinate system would be the polar coordinate system with radial r. We write it down, r theta. Symbol. Equal symbol. Yeah. R theta. Instead of x and y. Instead of x and y. Okay. The polar coordinate system, comma, the radial coordinate is constant. You know, r equal to L. The only one that varies is the angular position. Position theta. Okay. So what we're going to get, we're going to, you know, we're going to see in the forces in, because, you know, because the radial position is constant. What about the radial velocity? What can we say about the radial velocity and the radial acceleration? So you should be able to answer this question. You can type there in the chat box.
Is it constant as well?
Huh? Well, think about that. Think about that. Okay, so let's I'm going to write down, let's go back to the drawing here, right? I'm going to call the radial direction as being r, right? Radial direction as being r. So here you go. I'm going to write that down here. We usually call it rho, right? But and it's a constant equal to L. What about the radial velocity? You know, and I'm going to here write that as V sub r, the radial component of the velocity. Okay, how do you write the radial component of the velocity? Huh? You know that the x component of the velocity is what? It's a differential equation, right? You go, x component of velocity, you know that is what? dx dt, right? We did that in the previous case. So what would be the radial component of the velocity? How would you write that in terms of a differential? In terms of something like that? Huh? Hello? You should know that. Radial component of the velocity is x component of velocity is dx dt, right? If you change the component to r, what you're gonna get? You're gonna get dr dt, right? And let's write that down. Don't forget that this is a constant, right? This is a constant. If you differentiate a constant with respect to time, what do you get? You differentiate, this is a constant. You differentiate it with respect to time, what do you get? Derivative of a constant with respect to time is equal to? You can write down there in the chat. This is an easy one. 0, right? So the radial velocity is going to be 0. The particle is not moving away from this radius. That's what's happening. Here you go. I'm going to Here's the position, right? I'm gonna copy this one. Later on, let's see here. Transparency. I'm gonna show you the direction is changing, but not the magnitude. Let's see, rotation. Can I? No, I can rotate in the other direction. I want to get this guy in the vertical direction. See that? The direction of the vector velocity is changing, but not its magnitude. Oops. Here you go, like that. Okay, here you go. The length of this vector is the same as the length of this vector, which is the same as the length of this vector. Okay. So the particle is not moving away from the circle. It's not moving in the radial direction along this whenever it undergoes the circular trajectory. Okay. If the velocity along the radial direction is 0, what about the acceleration along the radial direction? You know? What about the acceleration along the radial direction? It's also 0, right? If the acceleration along the radial direction is 0, it means also what? That the net force along the radial direction is also 0. You know, the net force along the I'm not going to put a vector symbol there because I'm dealing just with the component now. Right? It's going to be AR. And that's going to be 0 as well. But wait a minute, there's more to it. We have this force here in the downward direction that has a radial component. And you have this tension here that also is along the radial direction. Okay, I should put, to make it more realistic, I should put my weight a little bit longer, right? Either the weight a little bit longer or the tension a little bit shorter. This radial component of the weight is going to be mg cosine of theta. Okay, mg cosine of theta. So here you go. Net force is going to be mg cosine of theta. Okay, minus the tension, which, by the way, ends up equal to 0. Okay, and we have this relationship between the tension and the angle, right? We can state that the tension changes as time goes by, as the mass oscillates back and forth. Okay. Now, what about radial direction? We're dealing with the radial direction, right? Now, what about the angular position? Angular position. Equation for the angular position. How do we deal with that? Right? Okay, so here we go. We're going to use theta. Here we go. We're going to use Newton's second law to find out how the theta angle changes as time goes by. Okay. the net force along the theta direction is going to be, there will be only one force along the theta direction. It's going to be this angular component of the weight. Okay, and that's going to be what? Do I have to write? Let's break it down into the components so you can see more clearly, right? Here you go. Here's the radial direction, right? Let me go. I'll make sure that this guy is parallel to the other one. Now I'm gonna project. You know, that's the radial component of the weight. And that's the tangential component of the weight. Okay, right angle triangle. And let's not forget that this angle that we see right in here is this, oops, is the same as the other, right? It's the same that you saw there. Let's see. Let me shrink it a little bit. This is angle theta. Here you go. I'm gonna put this mg here on the left side so you know that's the mg. That's the r component of mg. That's the theta component of the mg. The theta component of the mg is mg sine of theta. Here's mg cosine of theta, mg sine of theta. Okay. So what we are gonna get here, the net force is going to be mg sine of theta only. That's because the tension doesn't have any tangential component whatsoever. Okay. And now we can go the next step. We're almost there. We're going to get an equation, a differential equation, right? For our, for our theta angle. Let's not forget that the acceleration in the theta direction is the differential of the velocity in the theta direction with respect to t, right? And what else we have to know? The tangential, that's the tangential velocity, right? But the tangential velocity, can also be rewritten in terms of what? This derivative can also be rewritten in terms of, here you go, this guy here, v of theta, can also be rewritten in terms of ds dt, right? I'm doing step by step here. I'm doing step by step here so you understand where everything is coming from. But in ds, what's the ds? ds is the arc, is the length of the arc. And the length of that arc is going to be what? It's going to be the length of the string times the angle theta. I'm going to put that between parentheses so you know everything here is being, right, differentiated. L is a constant. And what we get the theta dt. See all the steps we have to go through to solve this problem? And now I can use what I got here in my differential equation, this differential equation here. right? I'm gonna use this v theta right here inside. The next step is, here you go. Step by step, okay? Step by step. Again, L is a constant. Okay, I'm gonna put that here outside. And now we are differentiating. Here you go. I'm gonna put this d theta dt outside so you can see better what we have. And here you go. Finally, I cannot do better than that. Okay. Erase it. Okay. And now we are left with this differential equation here. The net force along the theta direction, right? And the mass times acceleration in the tangential direction. That's our differential equation we have to solve, but there is one more step that you can take it to simplify my equation. Here you go. I'm gonna cancel this one here. I'm gonna do, can I do better than that? Let's see here. Yeah, I did cancel. I'm gonna put the L on the other side. Okay. And I'm going to reorganize, reorganize my equation here. Switch sides, okay. And that's the differential equation you have to solve to find out the equations of motion of my pendulum. You already have half of the equation of motion of the pendulum. Okay, the first half of the equation of motion of the pendulum, which is the radial coordinate, is this one right here. Okay, r equal to a constant, which is the length of the pendulum. But what about the theta angle? What about the theta angle? The theta angle is something that you have to solve. It's a little bit more complicated. Before we start solving this equation here, let's compare to what we had before. Before we solve the above equation, the above differential equation, let us compare this differential equation, right, with the differential equation we got for simple harmonic motion, okay? So that's it. Let's go back here. Where is that? Where is that? Go back, go back. Yeah, here you go. That's the one we want. Okay, let me see one thing. I believe that there is a missing. Oh yeah, there is a missing something here. Okay. Yeah, there's a missing sign here. Let us fix that. Let us fix that. Let's go back to the drawing. Okay, let's go back to the drawing. Can you pick up where is the problem? There's a mistake there in my equation. Okay, nobody picked that up, right? I just picked that up right now. Can you tell me where is the mistake there in my equation? I'm gonna give you a hint.
Is it negative mg sine theta?
Yeah, why is negative? That's the next question, right? Right, that's the next question. Why is negative? Think about that, why it's negative. I'm going to illustrate here why it's negative. Let's see, where is my x hat? I'm gonna use, let's see here. I'm gonna do like that. Yeah, it is negative, but then you have to ask yourself why it's negative, right? Why it's negative. I'm gonna copy this guy here. And I'm gonna paste it right in here. Okay, here you go. It's difficult to do a theta hat here in PowerPoint, so I have to do it in the Word document, okay? Here's the theta coordinate, and here's the theta hat. The theta hat vector. I'm going to draw the theta hat vector. The theta hat, the positive direction of the theta hat should be in the counterclockwise direction. Do you see here the unit vector theta hat? Everybody see that? Right? The unit vector theta hat. Theta hat has this direction right in here at this spot. If you move, don't forget that the unit vector at this spot, theta hat has this direction. At the other spot, theta hat is going to have this direction here, right? Everybody can picture that? As time goes by, depending on the position of the particle, theta hat is going to change. Ideally, I should put it right in here. See, that's the theta hat right in here, right? That's the theta hat right in here. It's a unit vector. Look at my component of the force along the theta direction. I'm going to copy and paste, right? Here you go. One is pointing in one direction, the other pointing in the other direction. See that? So that's why this guy must be negative, because it's pointing in a direction opposite to the other. I can even put it, I'm going to label this guy mg theta subscript. Okay, mg theta subscript. And put the symbol here. Okay. Mg theta subscript. So the mistake is right in here, right? Mg sine of theta. Right in here as well. Any other place? This is in the positive r direction, so that's correct. Okay, this one should be mg sine of theta. Here you go, must be g over L sine of theta. Okay, now let's compare that. Put this equation side by side with the other one. Right? So here you go. Here's the x. Okay, I'm gonna highlight it here. And here's my x. Here's my theta. I'm gonna put in a different color. Both face, but a different color. And here is my theta. Are those two equations the same? Suppose that I call this guy x. I call this guy x. Suppose that I call this one here k over m. Do you have exactly the same equation or not? Here you go. Suppose instead of calling theta, I call x. And suppose that instead of calling g over L, I call k over m. Are those two equations exactly the same or not? That's easy to answer, right? That's easy to answer. It's not the same because you have a sign here. See, you have a sign here. Strictly speaking, those two equations are different. Strictly speaking, those two equations are different, but we can make this equation similar to this one. And that's what we're going to do after the break, okay? In the 15 minutes from now. Let's do that. Let's take a break before we get burned out. Assuming that we are not already burned out now. But think about that. We know the solution for this equation. And now we want to solve this equation here. How do we solve this equation? Right? How are we going to solve this equation? There is a way to do that. And we're going to talk about that in 15 minutes from now. Break. Q is 10:31 right now. Break Q is 10:46. Any questions before I go for the break? Okay. I do not know. Are you folks seeing that for the first time, or some of you already must have seen that before, right? Let me hear from you, feedback from you. Are you seeing those?
Online before.
You have seen what online? Is that?
Yeah, on a YouTube channel.
Ah, YouTube. Okay, but did you take a course on that before, or just you did that on?
No, I did it on my own. I was just watching videos and I seen it.
Ah, okay. Is that the similar treatment that I am doing here? Is that similar to what they did in the YouTube?
Yeah, there's little differences, but yeah, pretty similar.
Okay. Before in the previous simple harmonic motion before in a previous course, yeah. Noah, let me see, Noah, you took with whom did you take the course, Noah? Noah, let's see, Noah Raymond, right? You took with Brian. Oh no, you took at Berkeley. Okay, at Berkeley is most likely your physics 37. They have simple harmonic motion, right, in the first physics, right, Noah? Yeah, you know, see that's the difference between some colleges, you know. Some colleges, the way I was taught, I got simple harmonic motion physics 37. Okay, but then there at LA Harbor, and I have a bunch of students from LA Harbor right now attending physics 39. They have a different curriculum. They teach physics, they teach simple harmonic motion only in physics 39. Okay, there is some reason for that, you know. There's some reason for that because they want to have simple harmonic motion at the same time as in the same course as wave motion. Okay, so but let's take our break. It's 10:33 right now, and 15 minutes from now is gonna be 10:48. Okay, so I see you in 15 minutes. By the way, don't forget. I'm gonna pause the recording. Don't forget to tell me about starting. You know, recording. That's when we come back. Okay. Resume recording. Good. So what's the trick to solve this differential equation here? The trick to solve this differential equation is to solve the problem for small angles theta. If the angle is small enough, if theta is small enough, we can state, you know, we have the following. Okay, here you go. And that we learn with when we study Taylor series, right? And then the question that we end up asking, you know, the question we ask, you know, we may ask is, what means small enough, right? Small enough angles. What means small enough angles? That's the question we may ask. As a rule of thumb, you know, small angles mean less than 10 degrees. That's a rule of thumb. But if you analyze the function of theta, sine of theta, you're going to see that it can be more than 10 degrees, okay? And I'm gonna do this exercise with you right now. Let me see if I have here in my notes. Here we go, let's see here. No, I don't, it doesn't look like I have, no, I don't have it. I'll have to do that in Excel to show that to you. You know, let me get, I'm gonna, so what I'm going to do here, I'm going to show to you that sine of theta can be approximated for theta. Yeah. under certain values, for certain values of the angle. And I'm going to make a table so you can compare it. And hopefully you will feel convinced, you will be convinced that's the case. I'm gonna do that in degrees first. Okay. Superscript. I'm gonna, but what matters for angles is not how the angle is measured in degrees. The real SI unit for angle is gonna be the radians, by the way. So I'm going to convert my angles from degrees to radians. Okay. Oops, and I gotta change this font as well. Times, here you go, radians. And then I'm gonna compare that with sine of theta and see how close theta is. I do not know if you have done that before, okay? When I was a student, nobody has ever, no instructor has ever done that to me, you know, showed how close the theta is with sine of theta, numerically speaking. Let's start with 0, right? And then you go for 1 degree, 2 degrees, 3 degrees, and so on. Here you go. I'm gonna go all the way up to 50 degrees. Okay. Everybody knows what sine of 0 is, right? What sine of 0 is? What's the value of sine of 0 degrees? What's the value of sine of 0 radians, right? 0, right? That's straightforward, right? But first, before we find out the value of sine, let's convert those degrees into radians, right? Let's convert that. Should be what? 2. We have a function here in Excel that can convert that, but I'm gonna do that myself. Let's see, 2 pi over 360, right? Times the angle is degrees. The angle in degrees, the value, numerical value of the angle in degrees is equal to the numerical value of the angle in radians, right? Is that right or not? Let's see. Let's make sure that radian, yeah, here, see the function. Let's see if it matches the Excel function. Yeah, it matches the Excel function, right? Radians of whatever is in degrees. It's a very simple relation. It's 2 pi over 360 or pi over 180 times the angle in degrees. Okay, so here you go. I'm gonna convert everything in radians. Why am I converting everything in radians? Because radians is the actual unit of angle. That's the real one. That's the one that is far more useful. Every computer program out there, most computer programs out there, most calculators out there, when you take the sine of a given angle, you have to take the sine of the angle in radians, okay? So here you go. So I'm gonna take the sine of radians. Someone is coming online here. Here you go. And let's see what's happening, okay? Sine of 1 degree. What do you get for sine of 1 degree? Do you see how they're close? The only thing that changes is this very last decimal, right? Right, but it has to be the theta in radians. The theta must be in radians. Let's see the percent. Let's calculate the percentage difference, so you can find out exactly what is the percentage difference that we have. Absolute value of sine of theta minus theta in radians multiplied by 100 divided by the exact value that you're looking for. We have this is small percent difference. It's 0.005%. This thing is negligible. In terms of physics, in terms of for practical purposes, anything less than 5 or 10% is considered negligible. Okay, anything less than 5 or 10%, and this thing is not 5%. It's even 0.005%. So let's go. Keep on going here. Next one, 2 degrees. do you notice that the percentage differences start to increase? You know, but it's still small at 2 degrees. You know, the percentage difference is larger, but it's still small. They're very close to one another. See that? I'm going to do even better. I'm not going to do absolute value. I'm going to do, you know, the actual value. So we can get a negative, so you can see whether you see which one is larger than the other, right? We're getting a negative percentage difference, right? According to my formula. Here you go. Do you see that? It's diverging, yes. The percentage difference is increasing, yes. But the percentage difference within those angles, 4 degrees, is very small, okay? Keep on going, keep on going. Let's see, 10%, 10 degrees. Okay, now we are starting to get a 0.5% difference at 10 degrees. But like I said, you know, it's still very small. Here you go, theta radians and sine of theta. We start to get a change on the 3rd decimal place, which is correspond to 0.5% difference. Let's see how far we can go. You know, what we start to get 1% difference at 14 degrees. Do you see that? And like I said, you know, negligible is something that less than 5 or 10%. That's the rule of thumb. Let's see where we can get a 10% difference. First, let's see where we can get a 5% difference. Okay, so here we go. 1.5%, 2% difference. See that? At 20 degrees. So at 20 degrees, we have only a 2% difference between sine of theta and theta. Okay. As we move on, let's see at 30 degrees, what we get percentage difference. We get a little bit less than 5%. So in principle, if we consider 5% negligible, we can use that approximation, sine of theta approximately equal to theta, up to 30 degrees. And maybe a little bit more, right? A little bit more. Let's see where 5% is. 5% is here at 31%, at 31 degrees. See that? And now, you know, it starts to diverge, okay? Let's see where's 10% difference we get. It's going just one direction because it's always negative, see that? 10% difference is around 43 degrees. Around, you know, we can round it up and say that's 45 degrees, right? 45 degrees is what? 11%. So that's how good that approximation that I showed to you is, you know? All the way up to 45 degrees, you have 11% difference. Okay, all the way up to 45 degrees. But like I said, most people say that small angles should be restricted to 10 degrees. But remember, at 10 degrees, you get a 0.5% difference. You can be even more tolerant than that. You can even come and say, look, I would say, you know, small angles can be considered 31 degrees because it's the 31 degrees that we get 5% difference. And if you are even more tolerant about your errors, you know, you can even push the envelope and say that is 45 degrees. You use those approximations whenever you do not have computer programs, right? Whenever you do not have softwares. If you're doing everything by heart, that's what you're going to use, okay? So let's go back to our notes. Did you get the idea? This exercise, what this exercise is all about? This exercise is just a way to test this approximation, to pass a judgment about how good this approximation is. That's what this exercise that I did is all about. And now, you know, here you go, we can state here, here you go. For angles less than 30 degrees, right? 30 degrees, we get an error of 5% on the above approximation. For angles less than 45 degrees, we get an error of up to, remember it's up to, right? Of up to 10%, 11%, right? That we got on the above approximation. So if we keep the oscillations of my pendulum within 30 degrees or even less, you're gonna get a pretty good prediction in terms of the angular position of your pendulum. So here you go. We use the approximation symbol, right? Here you go. G over L theta. There you go. And now we have an equation that's similar, a differential equation that's similar to the other one. Okay. Here you go. This one here. Because they have a similar format, they have the same solution. Okay. So we get that. Let's get the solution that we had that before. Cosine, let's see here. Cosine, here we go. Right here. Okay, it should be theta. Theta naught. Theta naught, instead of the square root of k over m, is going to be square root of g over l. Okay. Okay, this solution assumes a theta at t equal to 0. At t equal to 0, equal to what? Theta naught, right? And what else? And velocity v of theta equal theta t equal to 0. That's the assumption that we have right here. Symbol. Tangential velocity. That's the initial condition. The above solution assumes this type. Okay. So let's take a look at the notes. Okay, here you go. Oh, the period. What about the period? No, the period is going to be, the derivation is going to be similar. I'm going to just write down, display the period there for you. The period of motion is going to be 2 pi square root L over G. So as the length of the pendulum increases, the period also increases. Okay. That's the angular position, right? If you want to get the other ones, v theta and acceleration of theta, you gotta differentiate this equation once and twice. Okay, and then we have the physical pendulum. I'm not gonna do the physical pendulum here. I will let you do that yourself. Okay, otherwise we fall too behind in schedule, but it involves rigid body. Here is a table comparing the differential equations. Here is the exact solution for the simple pendulum. Here is the exact solution for the physical pendulum. Note, see that where I have m in the simple pendulum, I have the moment of inertia I for the physical pendulum. Okay. And we still have sine of theta here. And of course, we use small approximations, small angles, small displacements. Okay, mg theta, mg d theta. D is G is the distance of the center of mass to the point of, yeah, here you go. The distance of the center of mass of the rigid body to the point of oscillation. Okay, that's what D is. It's not a differential. Angular to linear, here you go. S, I can rewrite that down in terms of S, which is the arc length. Okay. Same thing here. Solution. Solution for X, solution for S. Here's S of the center of mass. But again, there's a relationship between S and theta. Period. 2 pi m over k, square root m over k. Okay. And here is your other solution. So how, do I have any questions before we get into damped oscillations? Okay, that's when the differential equation becomes more difficult. Okay. But it still can be solved. I did that in physics 38. And I'm going to, I did something like that for physics 38. And I'm going to do that for the oscillator, for the simple harmonic oscillator. So let's let's see how what I mean by a damped oscillator, right? What we can consider a damped oscillator. Okay, here you go. We have the case of the mass in the vertical direction, right? Which is a problem similar to, with a slight correction, with a slight change in the coordinate system compared to the motion in the horizontal direction. Okay, so here you go. Suppose, let's see here. Here you go. I made a change of coordinate system just by, if I put this guy inside a liquid, if I put this mass inside the liquid, we are going to have a resistance, a resistive force to the motion of this mass. Okay, if the velocity vector at this instant of time is right in here downwards, if the velocity, right? There will be a resistance that's going to be contrary, a resistive force that's going to be contrary to the velocity vector. And that's what the resistance force is all about. Okay, so here you go. You know, this problem is similar to that of the skydiver. Okay, if you have a fluid resisting the motion of an object, the resistive force is going to be proportional to the velocity. Okay, so let's see here. I'm thinking, okay, so here you go, and then what's going to happen? Here you go. Let's write down the equations of motion, the differential equation. Here you go. Damped motion. Mass subjected, you know, a mass attached to a spring and submerged in a liquid, will experience a resistance, resistive force that is proportional to the speed tweet speed, okay? In other words, here you go. The situation is gonna be like that. Let's see, net force. I'm gonna get the other one. Let's see here. Okay, it's gonna be something like that. Let's see here. Net force. Okay, here you go. Net force. Net force is going to be the force of the spring plus the force of the resistance, the resistive force. Force of resistance, okay? That's the buoyant force play. Yeah, it play a little bit, but I'm gonna make a simpler solution. Yes, it does play. It does play a little bit, but let's neglect that to make the problem simpler. Okay, Sha? Yeah, it does play. That's why I put the buoyant force in there. Okay, that's why I put the buoyant force in there. But I'm going to neglect the buoyant force, so you can have a easier solution. Here it goes. So let's see here. Let's mg. Okay. Yeah, that's right. We have a buoyant force here. We have this. Okay, here you go. Buoyant force, weight, and this is the spring, the elastic force, right? And this whole setup is in the. We're actually, we are not neglecting the buoyant force. What we are doing is that with the buoyant force is constant, right? Because the volume of the matter remains constant. The buoyant force displaces the original origin of your mass to a different position, this y dot prime. So that what's happening here. We're not neglecting the buoyant force. We're just making a change in the origin of the axis. Okay. So when we displace the mass, here you go, we extend it from the new origin of your coordinate system to this position here, why not? And let this guy, we're not supposed to have the velocity here. The velocity should go in the next one. Sorry for that, folks. Here you go. Should be, let's say the velocity is now upwards, right? Yeah. I release the mass is moving upwards, and now we have this resistance force here. Here's the spring. We still have the buoyant force right in here, but this buoyant force, is gonna cancel out in my new coordinate system, with my new origin. Okay, so here we go. This resistance force is a constant times the velocity, contrary to the direction of the velocity vector. Here is the velocity vector. Right in here. Okay. Okay, so we are left with the following. Go. Force of the spring, resistance force, one more coming. 11:20, we have 10 more minutes to go. It's a one-dimensional problem. Okay, I'm going to put that as a y here, and that's going to be y hat. Okay. And what else do we have? Here you go. The spring. The force of the spring is going to be what? Minus ky. Oh, I didn't put minus. I'm going to put minus here. Y hat. The resistive force is going to be minus a constant speed. What this v is the speed, okay? And I'm going to put the v hat. The v hat. Oh, what did I do here? Close it. Running out of time. Here you go. Hat. Unit vector in the velocity. Okay. And this velocity is gonna have a y hat, generic y hat direction. Okay, so let's go back here to my notes. This one. Okay, so we have a negative sign on both sides. Okay, so let's see here. Now we have a scalar equation. It's going to look just like that. We do not need this y hat anymore. I'm going to put here on the left, on the right side. Okay. And now we know how to solve this equation. This equation we know how to solve, right? The question now is how to solve this equation with the second term. That's the question. That's the question, right? So let's go back to, we can here write, I put dx dt, right? There I'm using dy dt. Here I'm going to use dy dt. dy dt. B is a known parameter. So damped motion. So here you go. Just another example. Treat that as another example. Okay. Find the equations of motion for a mass subjected to a spring of force constant K and drag by a fluid, right? So I'm going to reorganize my equation in a different fashion. Okay. And that's what I did here. And then you do the same reasoning that we did before. Okay, what we have here, you go ahead and look at the equation and see what the equation is telling you. This equation is telling you that if you differentiate my function once and twice, we get back the same function multiplied by a constant. That's what this differential equation is telling you. That's what this differential equation is telling you, right? But now we have this added differential term. We have this added differential term. What we had before that we solved was something like that, right? Before we had something like that. Now we have something slightly different, but the solution is no different. The way to solve this equation here that is more complicated is no different than the way to solve this equation here that's less complicated. You have to look at it. You have to look at to find a function in which when you differentiate it once and when you differentiate twice, you get back the same function. Okay. And what type of function behaves like that? Okay, it's the exponential function, just like before, right? It's the exponential function. Let's do it step by step, right? So which function obeys the above? Just like before, it's an exponential function, but it's going to be a different, the exponential function with a different argument. You go y. Did I put a exponential minus, let's see, RT, right? Minus RT. Another possible solution would be a plus RT. That would be another possible solution, right? But that shouldn't work because you're going to see why. Because if you put a plus exponential plus RT, the amplitude of motion is going to increase instead of decreasing, okay? In this case, you are losing energy. In this case, you're losing energy, but not in this case. In this case, you're gaining energy. So although this function is a solution to the differential equation, it's not a physical one. Okay, so we're going to eliminate this solution. And what's next? we're going to find what R and A are by differentiating those terms. Okay, we're going to get minus R here, right? Second derivative is going to be another R. Okay, and should be a minus R square. The whole minus R between parentheses. When we square a negative number, we get like that. Oh, did I put an A there accidentally? Okay. All right, here you go. Exactly what I got here. And now we have to substitute those differentials in the differential equation. Go copy and paste. This one goes right here. This one goes right in here. Oh, and let's not forget to replace that here. Okay. This R that I wrote in there is not a variable, okay? It's a constant. Okay, in the next step, we can cancel the exponentials. Exponential, not just the exponential, but also the initial amplitude A. And then what we have this quadratic equation in R. We have this quadratic equation in R. We know M, B is given because that coefficient that goes in the resistive motion, right? The resistive force, and we have K, that is the spring constant. We do not know R, but we have this second order, this quadratic equation that allows us to solve what R is. Here you go, right in here. We are here at this step. That's how we solve for R. R has two solutions, right? Let me write that down here for you. R is going to be given by minus B, and then we have a plus and minus. Let's see if I can do that. No, oh yeah, good. Square root. Yeah, square root. Let me erase everything here. B squared. It's not extending, huh? Minus 4m. Oh yeah, he's extending now. For a C. Let's see if I can get this guy here. Okay, now we got it. Over 2a. Okay, so let's go another step here. Is everything all right? Do you see anything wrong here? For a B, yeah, okay. B squared minus 4ac, right? 4ac. My B is minus B. Okay, so here it becomes plus B. Here becomes B squared. Okay, minus 4mk. That's the, and we have two solutions. One is going to be a positive square root. The other one is going to be a negative square root. Let's compare that with my notes. You go, yeah, b squared. Let's put that side by side. We don't have to keep on switching back and forth, right? Compare it nicely side by side. Okay, same, right? And now let's look at the possible, let's analyze those solutions. Okay. What if b squared is greater than 4mk, right? So here you go. What if this term here greater than zero, greater than 0? Okay, or let's say b squared greater than 4mk. If b squared is greater than 4mk, okay, we are going to have, let's get that here, here you go. Let's write that down. 11:30 already, huh? Let's see. Let's well, you know what? Let's take a little break now, right? It's 11:30. I'm gonna use the rest of the time to 2 o'clock to finish that, and then we have a sort of a virtual lab tomorrow. Okay, it's 11:32 right now. We can have lunch right now, and then we meet again at 12:02. Okay, break. Do you have any questions? Any questions so far? So now it's just a question of analyzing this solution here for certain conditions. Okay, it takes time, but it's nice to look over it to see how it goes. Okay. So I will see you at 12:02, and I'll leave this screen on, and I'm going to turn off my camera and my mic. Okay. If you don't have any questions, okay. So see you in half an hour. Okay, thank you. Looks like I forgot to record. Yeah, thank you. Thank you, Jen. Yeah, we missed a big chunk here of time. Okay, so that's what we're doing. Okay, so just summarizing, right? We got this solution here for the damped oscillator, and we are looking at two different conditions. The first condition is in which this square root is a real number. When the square root is a real number, when b squared is greater than 4mk, you are going to have a decreasing exponential decrease in the amplitude of the oscillator. Okay, it's going to decrease exponentially as time goes by. It's going to be either something like that or something like that, or a linear combination of both. Okay. However, you get a much interesting solution if the b squared is less than 4mk. When b squared is less than 4mk, then you're going to have, yes, an exponential decrease, but you're also going to have an oscillation due to the fact that the square root here becomes an imaginary term. Okay, and like I said, we can go ahead and see in a graphical fashion how it behaves. Okay, so I'm going to do like exponential in this specific case, for these specific numbers, we are going to have an oscillation combined with an exponential decay, because b squared minus 4km is a negative number. Okay, so here you go. Exponential, that's minus b times t. I have those things almost by heart, right? Divided by 2 times m. Okay, that's the first term. Let's see, this guy is supposed to be a constant. E is not a constant. A is a constant. Okay, and then we are going to have the second term. That's going to be a cosine, right? Cosine of square root of b squared minus 4 k m divided by 2m, right? Go. 2m. Let's see if I got everything right. Yeah, here you go. It looks like I got everything right. No, what's the problem? It's giving me a square root. Let's see. It's square. Let me put my equation here on the side. Here you go. Okay, let's see, square root. Everything here is inside the square root. A and b squared, the c should have a dollar sign right in here. A, b, and c should have a dollar sign. Oh yeah, I have to have a t as well that I didn't put. Maybe that's the problem. All right, let's see. Okay. Yeah, I don't see any problem. Let's see. No, he's still giving me an error. Why is that? Oh, I know why. I know why. Yeah, the reason is that Excel doesn't take the square root of a negative number, right? That's the reason. So I have to put ABS here. Okay, and now he will be able, those are the little tricks, right? That we end up discovering in Excel. So now we have, okay, remember, because this guy here is a negative number, Excel and many other programs out there does not take the square root of a negative number. That's why I was getting that error message, right? That's why I get even better. I'm going to do the following. I'm going to simplify my formula. Instead of putting a square root of that stuff here, you know, a big stuff that I have here, I'm going to put square root of that to simplify it, right? And that is going to be a constant. Yeah. And now let's, you know, increment it by 0.1 second. And let's see if we can. Oops, he didn't like it. Why is that? Oh, that's why. That's why. So that is okay. This one here is supposed to be a constant as well. Put the dollar sign there. See, that's debugging, right? That's what we call debugging. Every time you write a computer program, you debug it. Now let's see if we can get a nice plot. If you don't have a nice plot, I have to adjust here the time scale. Insert. Oh, I didn't get any oscillation whatsoever. Well, we got a little bit of an oscillation. Yes, we did get a little bit of an oscillation because it went in the negative direction. Okay, we did get, see, it went in the negative region. If I decrease the damping coefficient, here you go, I get a little bit more and more of an oscillation, right? Go back to 2, see? Okay, here you go. Now I have 2 oscillations, see that? I keep on decreasing it, right? I have more and more oscillation. And we have the envelope, the exponentially decreasing envelope. Good. Everybody understand what's going on? Let's see what happens with the K. Okay. The K becomes weaker. No, it doesn't change much, right? Through 2, here you go. Yeah, so let's keep on 10. But as B becomes weaker and weaker, you get more and more of an oscillation. See, we're coming to a point where the damping coefficient becomes almost negligible. So much that the amplitude remains almost the same, right? It's barely perceptible. It's barely perceptible. Okay? Barely perceptible. If I decrease even more, it doesn't even gonna look like that it is a damped oscillation. But let's go back to, to stronger damping. What happens if we change the mass? Let's see what happens if we change the mass. Okay, just we have a shift, right? Somewhat of a shift in the time direction. Okay, let's go back to 1. I like that. And what I want to do, what else do I want to do? I want to put the envelope there, and even better, I am going to extend. I don't like going only up to 7 seconds, 8 seconds. I'm going to put a longer time interval here. Here you go. What I have right now, 27 seconds right now. Let's make, let's see. Yeah, okay, so we stop it here. Yeah, it doesn't go the way I want. That's what I'm doing 2 different. Okay, so now, okay, here you go. It's too much, right? But let's decrease the damping. If we decrease the damping, we'll be able, oh yeah, to see more. Nice, here you go. I'm gonna get a better 0.5. Just increase a little bit more. The listing is a little bit too much. Yeah, you see the oscillations, right? And now what else I'm gonna do? What else I'm gonna do? I am going to plot the envelope. Let's see. Like that. Okay, but I want just to put the envelope there. And I'm going to plot the envelope so you can see that the amplitude is decreasing, right? So I'm going to, let's see here, I'm going to do that. I'm going to no, it doesn't like it. Let's see if it, nope, doesn't like it. So let's put it back there. And then I have to, what I have to do, I have to add, X that's the X, and that's gonna be the Y. Okay, okay, cool. Let me see what happened here. Oh, that might be a. Let's see here, 2 minus. Ah, interesting. Let's see. Yeah, 2 exponential. Well, it's supposed to be an envelope. Let's see what's going on here. Interesting. $27. Huh, you went all the way up to 300. I don't have a clue why he did that. He plotted something wrong here. I do not know why, you know? So let's see. Well, let's start from scratch. Let's start from scratch. You know, like that. You go, insert. Now we should get the right plot. Yeah, now we got the right plot. See that? I do not know what Excel did there before. Yeah, I really don't have a clue. I think, okay, I think I know what happened. Yeah, okay, I know what happened. Now I know what happened. Okay, now you have the envelope, the exponential envelope that I want to show you. Okay, so there is an oscillation back and forth, right? And this oscillation is bounded by this exponentially decreasing envelope. We could plot another negative function right in here that you would be able, that the whole thing would be bounded, right? So here you go. Copy it. Paste, insert, copy it. Okay. Minus that FG, G2. Right, here you go. And then we are going to plot all those three functions. Yeah, the damped oscillation is bounded by this exponential decrease here. One exponential decrease is the negative of the other exponential decrease, okay? That's what we get for whenever this value here is negative. That's the type of behavior you get when we have this, a negative value for that relation, okay? Now let's see what happens whenever we have a positive value for this guy. Okay, a positive value for that guy, and let's see. Then, okay, now we have a positive value, right? Whenever you have a very, oh no, this one is not positive. This one is negative. Now it's too large. Let's see, 9, 8, 7, 6, 5, 4. Okay. Oh, now we have an oscillation. So 5. I didn't notice that. 6, 7. Okay, we stay right here. And maybe 6.5. Yeah, 6.5. Okay, so here go, no oscillations, right? And let me see if I can do better than that. I don't like, let's see. Yeah, I'm gonna cut down to all the way up to 5 axis option right here. So you can see the exponential decrease better. I'm not going to use this one. Okay, good. The exponential envelope ends up almost coinciding with the actual motion, right? Which one is the exponential envelope? Yeah, the other one is the exponential envelope. we are getting. Okay. So those are the solutions that you're gonna get for a damped harmonic oscillator. 1245. Any questions about that? Some functions you have to plot that in Excel to understand how it behaves. Okay, some functions you have to plot in Excel to understand how they behave. Okay, and I think that's nice that we have those spreadsheets nowadays, because we can visualize some rather complicated functions. And you can keep on playing with the parameters to understand how a given solution behaves. Okay. Any more questions? We have, like I said, we have similar solutions for certain, circuits, right? Circuit, electrical devices out there that has a capacitor and a okay, Robert, thank you. Is uploaded. Yeah, no, the homework is not uploaded on Canvas, Daniel. You have to go straight to Wiley Plus, okay? I didn't have the opportunity to. No, it is there. Other students saw it, right? Check with the other students; they were able to see it. Does anybody else? Are you having problems visualizing the homework in Wiley Plus? I fixed that at the beginning of the session today, Daniel. Earlier on, around 8 o'clock, 8:30. Did anybody else had any problems with the? Are you having any problems with the Wiley Plus? Yeah, double check that, please, Daniel, and let me know if you still have any problems. Okay. Still not there? Let's see what's going on. Anybody else can tell me about this Wiley Plus? What you see there in Wiley Plus? Let me log into Wiley Plus. Here you go. Here's Wiley Plus. I didn't. Yeah, June. Okay, and due June 27. Okay, and I need to have a feedback from other students, please. If you're seeing it or not, Daniel is having a problem. Let me go through the attendance here. Toby, can you check? Do you have a Wiley Plus already, Toby?
Yeah.
Yeah. Did you check? Can you see the homework there?
Yeah. Well, at first I couldn't, but now I can.
Okay. Maybe Daniel. Maybe you have to log off and getting the, and log in back again. Okay. Okay. Try to do that, Daniel. And let's see, Pedro, were you able to log in Wiley Plus, and do you see the homework there?
Sorry, I was eating lunch, but I have not gone to it.
Do you have access to Wiley Plus, Pedro?
No, Professor, I haven't tried it.
Oh, you haven't. Okay.
I'll try it tonight, like once the Zoom is over.
Okay, thank you, Daniel. Thank you. Yeah. So Daniel finally saw it. Okay. So what I want to do, I want to take another quick break. Okay, 12:48 right now. Let's take just a 10-minute break this time until 1 o'clock. And so we have time to go to the restroom and drink a little bit of water. Okay, another break till 1 p.m. Okay, and then we go for 1 hour. And those students that are trying to add, stay after 2 o'clock during my office hours. So you can figure out how to get you into the course. Okay?
He's been at it.
I can't hear you. I can't hear you. What did you say? Okay, so we have like how many students? We have 3 students, right? Who are trying to add. Yeah, Olivia, Sarina, and Alexis. You know, stay after 2 o'clock for my office hours, and then I'll try to help you out with the add code. Okay. Let's have our
Thank
break
you.
now. No, welcome. Okay, yeah, let's have our break now, and I'll see you in 10 minutes.
Yeah, Bez.
Okay, I'm back here. And let's start recording. Let's see what else we can cover today. And let's so what we did, simple harmonic motion, right? Simple harmonic motion. And at SHM, we did a simple pendulum. Okay. Damped. SHM damped. Damped case. What else can we do? There are other possible, the other one we have here is the forced oscillation. The forced oscillation is very extensive. The derivation is very extensive, believe it or not, okay? It's possible to do that. You see how much we have here in terms of derivation? Many books out there don't derive that. They don't go from the beginning to the end. They just give you the answer. But that's how it's supposed to be done. Okay, well, we're going to try to do that in the next hour. Okay, and so you can understand where those equations come for forced oscillation. So here you go. Now, the next type, forced oscillations. Okay, with damping. Forced oscillation with damping. But by the way, where should be harmonic. Force oscillation with an harmonic force. Let's put it this way. It's better, with an harmonic force. When we talk about forced oscillations and we don't specify it, it's as though it could be any force. But every time we talk about forced oscillation, we are talking about an harmonic force that acting on the object. Okay, let's go back to our original, here you go, net force, right? That's what we had before. Here you go, here's the force of the spring. Here's the resistance, apply it. And then the forced oscillation is another force. And let's put everything in terms of a scalar. Okay. Since I am using the y position, let's put as a y as well. And then we end up, the net force should be the force applied by the spring, the force, the resistance, right? And then we also would have a term here that varies in a harmonic fashion. Here you go, omega. I'm going to do the same notation that I have in my notes there. Let's see if I have that. Yeah, I put sine, right? And I have sine here as well. So it is as though think about how you can provide something like that, Let's get my drawing right in here. It would be something like that, but with one more thing, with one more thing. We can have a platform that oscillates back and forth. See, this is a movable platform. That's what the forced oscillator is all about, okay? How we can visualize a forced oscillator in this way. I'm gonna write that down here. forced oscillation. Like that. So what? How can you visualize that? You know, by getting this platform to move back and forth. That's one way. Okay, I can put here you go. A force that makes this platform to move back and forth. That's one way to visualize it. With that constant, with that angular frequency omega. Okay, so it's not fixed. This platform is not fixed. It's moving back and forth. That's one way of visualizing it. And now we can start working on this differential equation. How to solve this differential equation? That's the key, right? You already know. Here you go. Look at the differential equations we have so far. We solved this differential equation. We solved this differential equation. And now we're going to attempt to solve this other differential equation. Okay. That's how we're progressing, right? I'm gonna put just like we have here. It's better, right? Put the differential term on the left side. Looks nicer. Put this other one here. And okay, like that. Here, for this one, you know, the first solution, I'm going to just write down next to it how it looks like. Here you go. That's the solution for the first differential equation. K over M X naught X and you know this other solution can be either there you go, one like that, right? Hanging there. Let's see, someone else trying to get in. Okay, can be something like that. Can be something like that. Okay, there are three solutions actually, but two of the three solutions behaves almost in the same way, or it can be something like that. Yeah, so I'm going to be specific, right? It's better to put the negative sign here so you can see the difference more explicitly. While this one is negative, this one is going to be positive. So let's here you go. And the other one is plus. Okay, like that. Three possible solutions. And what about this one? You can see that we have, we always have a cosine of, almost always, right? Have a cosine term. Even the exponential can be sought in terms of a cosine and sine. Okay. So if all those solutions that we see here involves trigonometric functions and an exponential that can be written in terms of a trigonometric function, it would be pretty reasonable to assume that a solution for this more complicated equation would involve a sine or cosine, a trigonometric solution as well. And then we go ahead and find out, substitute it and find out whether it has or not, okay? If there is any conditions that need to be obeyed, okay? So here you go. Here the condition that we have. Here's the possible solution that we can have. That's the key about, then the thing about, I put X here, right? Yeah, I gotta put Y. That's the thing about differential equations. In order to solve differential equations, we gotta use, basically we have to use a gas, okay? And we're going to try, I use what there? I use a cosine solution here. Let's try a cosine, and we're going to use omega and see. And to be as much general, as much generic as you can, let's put a phase term here in this. We are not going to use Y naught. We are going to use a more generic amplitude. Instead of Y naught, let's use this more generic amplitude. Remember, because it's a forced oscillation, the oscillation might be increasing in amplitude, right? It's not going to be necessarily restricted to the original amplitude Y naught that you had. And in this solution here, we are assuming that this omega is the same as this omega here. But we have two unknowns, A and phi. A and phi that we hopefully will be able to determine. And believe me, it's lots of derivation here. It's very extensive. I'll try to do as quickly as possible. Here you go. We're gonna get the x dt, d2x dt2, and so on, right? Let's start. In my case, it's gonna be dy dt. Dy dt is sine minus omega. Okay. And d2y dt2. Okay, and then I'm gonna get cosine here. We try the solution. The idea here is to try the solution. Let's see if we get. Let's see if this solution satisfies the equation. Basically, that's what we're doing. It involves lots of hard work. Okay, and you're going to see it involves lots of hard work. I'll do that here with you. And substitute one by one. d2y dt2. Go. Right, d2y dt2, the y goes right in here. Okay, and okay, so next step. Okay, here you go, Emma. Go inside this parenthesis. Negative, we have this negative that's going to cancel out with the other negative on the outside. And go. Let's compare, right? Whether we're going in the right direction. Let's see here. I didn't put it. Well, first I'm expanding this cosine of omega t plus phi. Okay. And then I'm going to do the same for the other ones. We use our trigonometric relation that we know. I'm going to put that between parentheses. And, you know, there are some solutions that you have no other choice, but to do the hard work, okay? But you could also use a technique called the phasor as well, like we did before in physics 38. Cosine of omega t, cosine of phi. Didn't like it. Okay, good. Cosine of phi minus sine of omega t, sine of phi. Sine of phi. Okay. This term here, you don't have to worry, but then we have to worry about that, right? So let's see if there's a simpler way of moving forward. Let's see. Yeah, I'm repeating here for the other ones. We have no choice here, so let's go ahead and you go cosine of omega t plus phi, just like we had before, right? Cosine of omega t plus phi, cosine of omega t plus phi. And then you're gonna have sine of omega t plus 5. Okay, sine of omega t plus 5 is gonna be quite similar, but not exactly the same. Let's see. Sine of omega t plus phi is what? Sine of omega t, cosine of phi, cosine of omega t, sine of phi, but then you must have a positive sign here. Let's see if I did it right. Yeah, we have a positive here, right? What I'm going to do next? We collect the terms that multiply sine of omega t and cosine of omega t. There's a reason why we do that, okay? So here we go. But before we collect those terms, let's first expand everything here that we have. So we can go. Okay. What else? Minus Ka on cosine of omega t minus Ka sine of omega t sine of phi. All right. I didn't, let me eliminate this parenthesis here. Okay, and then I gotta do the same for this term. Here you go. Here you go. Here you go. Like that. Yeah, it doesn't go in the same line for some reason. And then what I'm going to do, I'm going to collect the terms of cosine of omega t and the terms of the sine of omega t. I'm gonna put the cosine of omega t on the left side and the sine of omega t on the right side. In the process, we are going to change their signs, right? Interesting. Huh, interesting. Okay, so sine, oh, there is this cosine of negative term. Okay, here you go. Let's put them in evidence. Cosine of negative right here. Cosine of omega t are eliminated from this inside. Let's see if we can we, yeah, we can. Let's factor other terms here. Can we do that? Anything else? And now I gotta factor the sine of omega t terms. Here you go. This guy goes here. I think it's very good to use this type of software to solve equations. Because it allows, because it cuts down on, oh, what did I do? On the possibility of mistake, of error that you can make. Here, I don't want the sign here anymore because I already put there on the outside. Why am I factoring cosine of omega t and sine of omega t? There is a very good reason for that. Okay, there's a very good reason for that. Let's make sure that I got it right before we move forward. You go. Okay, I put this term here, cosine of phi, right? Let's do that too. M omega square plus K. M omega square, M A. Oh, I have already the A here outside. Okay, good. Square, and there is a sign difference, right? But M, okay, K minus M omega square. Okay, good. So it's just a matter of commuting these terms. D omega sine of phi. But we have a negative sign here. Let me see why I have a positive sign. Let's see. Did I make any mistake? Help me out here, folks. Are you doing the math as well? They're on your side. I have minus, plus, and minus. Minus MA plus KA minus B. Okay, minus MA. I'm gonna put side by side here. See? Okay, KA, okay, this KA goes to the other side, becomes positive, yes. But we have this MB, this BA omega that okay, BA omega. Here is negative, here is positive. Let's see. Maybe oh yeah, that's right. I didn't pass it with the right sign, right? So here you go, the mistake is right in here. Good, the mistake is right in here. This one goes to the left side, has to change the sign. Do I have any other mistakes here? I have m omega squared. Why do I have this m omega squared here? Okay. If I don't have any omega, oh yeah, because I passed this one here. Okay, good. M omega squared. Okay, good. K A sine omega t. Okay, that's the 1b omega. Okay, good. Sine of 5. There's one. Okay, and this one went to the other side. That's good. We're in good shape here. And K, okay, minus m omega is, but we have to have a negative here. Okay. F naught a sine of 5 plus KA sine of 5 b omega a cosine of, okay, good. So it seems that we have everything right. So why am I doing that? Why am I separating in terms of cosine of omega t and sine of omega t? There's a reason for that. There's a reason for that. Okay, and the reason is that those two functions, sine and cosine, they behave like perpendicular vectors. Okay, they behave like perpendicular vectors. And because they behave like perpendicular vectors, we can come up and say, look, this term here that's being multiplied by cosine of omega t is going to be equal to 0. Okay? And this term here that's being multiplied by sine of omega t is going to be equal to 0 as well. And it's possible to prove that those two functions are perpendicular to each other, okay? All you gotta do is to integrate sine of omega t with cosine of omega t dt. And you're gonna always get a 0 in there. So that's how we prove that a function is, one function is perpendicular with respect to one another. And when you do something like that, here you go, you can go ahead and you will be able to solve for those two unknowns. Let me highlight the unknowns so far. The unknown is the phi and the amplitude. The F naught is the maximum force that are being applied to the system. So it is known as well as B and omega. This force has a angular frequency omega naught. Okay, so now what do we have? We have two unknowns for two equations. Okay, two unknowns for two equations. In principle, we can solve this system of equations. The two unknowns as A and phi. A and phi. Okay. Two unknowns and two equations. In principle, we can solve this system of equations. And that's what the key in solving this problem is all about. It's about solving this system of equations. Okay. The easiest one to solve is for phi. That's the easiest one to solve. Whereas the second one here is still involve the phi, is still involve the two unknowns, right? So let's solve this one first. Every time that you're solving a problem in physics, make sure you don't get yourself burned out trying to solve the most difficult part of the problem, right? Start with the easiest one. The easiest one is this one here. Okay, I'm not going to worry about the second one yet. Okay. And I'm going to pass the cosine of 5 to the other side to get a tangent. Huh. I hate that. Let's see here. I'm gonna, here you go. Now I got it. Right? I don't need a parentheses anymore. Okay, I don't need the parentheses anymore. I can divide this term by b omega. And that of my tangent of phi turns out to be. So in principle, I am able to solve for that unknown, which is the phi. The key now is to try to solve for this one. Note that I don't have tangent here. I have sine of phi. Here, not only sine of phi, but I have cosine of phi as well. Okay. We can, here you go, we can try. Let's see if we can arrange this equation downstairs here in such a way that we can use the solution that we have right in there. Oh, how do we do that? You know, let's factor in terms of sine of phi. Okay, Ka. And I'm going to simplify even further. I'm going to put that A here outside. I will make sure I keep it in boldface because it's signaling that this A is, oh, wait a minute. Looks like I made a mistake. Yeah, I made a mistake here. Whoa, 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 whoa. There is a plus here. Don't let it go. Here you go. No, it's a plus. Yeah, it's a plus. All right. Watch that out, right? I'm factoring only this term here. You don't have A everywhere. Okay. Can I get a tangent of phi here? Okay, can I get it? If I can get a tangent of phi here in this term here, I will be able to solve this problem very easily. I will be able. And let's see if we can get a tangent of phi here. I'm going to divide both sides of this equation by cosine of phi. Okay, I'm going to divide that by cosine of phi. I'm going, oh, gosh, hate that. I'm going to divide the other term by cosine of phi as well. Here you go. This first term becomes sine of phi. And this term of phi is going to become 1 over cosine of phi, which is second, right? I have tangent of phi here. Yeah, I do have tangent of phi here. But here we have 1, but I do not have tangent of phi here. Okay? So we got nowhere trying to solve this system of equations using this technique. We will have to think about solving this problem in a different way. Okay? That's what we have to do. And then there is this important trick. Those tricks are hard to find. You know, there are 2 tricks here in the solution of this problem. The first trick you saw right in here. Okay, to get the coefficients of cosine of omega t and sine of omega t. That's the first trick. Difficult to figure out. I've never seen a book that teaches something like that. Okay, maybe there is some books out there that teach that. Okay, the second trick now is how to solve the second equation if you do not have a tangent of phi term here. Okay, but there is a very nice trick that you can use in this, that's hidden right in here in this term. Okay, instead of writing tangent of phi, go back to your term that we had initially. Go back to the sine over cosine, right? And then you're going to see what I mean. Sine, oops, sine over cosine. Here you go. Can I get that? No. Yeah, let's leave it this way. And don't forget to put the cosine here as well, right? Cosine, 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 cosine. Oh, here you go. Here's the cosine. Here you go. Ooh, here you go. Here you go. So there is a hidden trick in this very first equation. And the trick is the following. I'm going to teach you this trick right now. Note that we have a ratio here and we have another ratio here. So it's very reasonable to state that sine of phi alone, okay, is going to be proportional to what is upstairs. A proportionality. And we do, you know, a proportionality, and then we do have a multiplicative term here that we do not know yet. I'm gonna call, you know, let's see, what do we want to call it? Little c, let's call little c. This is not an assumption. This is not an assumption. This is real life. This is what this equation is telling us, okay? The other part of the equation, to make everything correct, is to recognize that we have a similar proportionality for the cosine. It is the same constant, right? Multiplied by what you see right in here. Okay? At this very moment, C is an unknown. Okay? At this very moment, C is an unknown. But if we can find the C, we will be able to solve this equation here, this second equation that you see right in here, either this one or this one. Okay? And that, let me just copy this one and paste it right in here. So you have a simpler one. So that's the trick. That's the second trick. That's what make some problems difficult to solve. Okay, there are some hidden tricks out there that you have to look for to help you solve the equation. So with this second trick, you will be able to solve this problem. And let's see what happens. But then again, like I said, you must know what C is. You must know what C is. Now I'm going to ask you, how can we find C from those two equations? Think about that. You know, there is a very obvious relation there that involves sines and cosines that allows you to solve for C. Think about that. What equation can I use to determine my proportionality constant C? I'll give you some time to think about it. Okay. If you manage to determine what C is, you will be able to solve the whole problem. Okay? Think about that. How can we determine C? Maybe I could substitute sine of phi right in here, right? Maybe. Maybe I could substitute cosine of phi right in here, right? But then I will have this single equation with two unknowns. That's not the way to solve it. What we need another equation that we haven't written down yet, that will allow us to solve for C. Anybody has figured that out yet? While you do that, Let me take a look at my notes, make sure I didn't make any mistake here. Think. I'm gonna, okay, tangent. Okay. Yeah. Anybody? Let's see. 1:45. We have 15 more minutes to go. Okay. We are almost done with this problem. Any volunteers to risk? What do you do? It's really nice if you can figure out, how to solve this problem on your own. I had to do that myself, Okay, the equation that would allow you to solve this problem is that equation that everybody knows from trigonometry, sine O. Huh, interesting. Sine square plus cosine square equal to what? Equal to 1. Equal to 1, right? That's the independent equation that we can use to solve for C. If we use this equation here we go. All I have to do is to square this term. Square this term. Oh, let's see. Square the other term. Right? And so for C. That's the little trick that has been hiding in there. Let's see here. I'm gonna get this guy. I'm doing step by step, right? That's why it's taking so long. B square, omega square. Now you go ahead and put C square in evidence. Okay, like that. And so for C. It's gonna be something like that. Hopefully I didn't do any mistakes. Okay, the C can be, it's gonna be a square root. Can be either plus or minus. There you go. It's gonna be something like that. All right. Now, let's finish solving this problem. Now that we found out what sine of phi is and what cosine of phi is. Let's see, here you go. Sine of phi something like that. Cosine of phi, it's something like that. Okay. And then we go ahead and substitute right in here. Ten more minutes to go. We go. Oops, no equal sign here. Right, we gotta put And oh man, equal sign here. No? That's going to be plus and minus, plus and minus, plus and minus, right? We have a pro. Yeah, that's right. Okay, so basically that what here you go. Let's see if we can do anything else here to simplify. Go ahead here, the notes. Here I did slightly different. I didn't use that third equation, but I did, you know, just like I said, just slightly different. Here you go, plus and minus, right? So I am at this point here. Okay, sine, here you go. Here's the sine of phi, cosine of phi. Okay. And let's see, wait, let me try to get into this format. How do you get into this format? The way to get into that format that you saw is by passing this term that see here inside the square root. When we do that, we have to square it. Okay. Let's see, wait a minute, I think I made a mistake. Yeah, I made a mistake, okay? Watch out for those mistakes of mine. Let's see, let's repeat what we have here. Here you go. Let's repeat what we have here. This is b omega. I'll put here on the outside, on the other side. Here goes this one too. In the front, right? So what was the mistake that I made? You know, I pasted the sign of phi in both terms, right? That was the mistake I made. So let's do it right. Here you go. Sine of phi. Oops. Yep. Even better, I'm gonna put this guy here inside. Yeah. Make it shorter. Yeah. I'll do the same here with this one. Make it shorter. B squared. Right? Like that. Sine of phi. Yep. I will. Sine of phi. Cosine of phi. Okay, here you go. Oh gosh, I put it, yeah. I want to put it here. Okay, so let's see what. Okay, so I have another b omega here. That's good. Yeah, okay. I don't need that. And now I can solve for a. I can finally solve for a in terms of the other terms. Okay. So we found what phi is, and now we can solve for a. That is all. Here you go. We can combine those two terms, right? We can combine with them. That's what I did. We end up having just a square root downstairs. There was no need. Let me see. There was no need to push this one outside, but I did that because it make it for a shortened equation, right? So here you go. Let's do what I did there. I will take this one out on the square root, combine with this one, becomes a square. And I'll do the same with this other term. Okay. This term is common with this other term, as well as a, so I can get both in evidence, right? As well as the plus and minus sign. I'm gonna put the a right in here. Let's see if we get lucky and simplify everything. Yep. The plus and minus, here you go. Yeah, the plus and minus is a common term as well, so I can put it just as plus. And we, oops, oh my goodness. Okay, so you're getting here, A can be solved with F naught and all that term here, okay? And that, let's get this F naught on the other side. Let's see, becomes minus plus, right? Because, and the A they're gonna be a square root there on the other side. Okay. And then later on in the next class, we're going to analyze how this function behaves. Okay. So far, we just did the hard work that was deriving an expression for the amplitude. Notice this amplitude, it can be either a positive or negative amplitude, right? So let's compare what I have there, what I have in my notes. Go. Yeah. Okay. The amplitude is always positive, right? Let's see here. F naught. Yeah. I can come up with another step. What you have writing here is exactly the same as you have writing here. So it's a square root, cancel out as a square root. Okay, so here we go. And we get what I have right here. Okay. And let's put the F naught here because we're talking about amplitude. What amplitude has to be always positive. So that's the solution that we want. Okay. So 156. I want you, for tomorrow, before you come tomorrow, start analyzing what, how this relation behaves, in terms of omega, in terms of the frequency of oscillation, in terms of the frequency of the forced oscillation. And you're going to see that has a very nice behavior. Okay. One little hint that I can give you is that if you have a system in which you have no damping whatsoever, B is equal to 0, what's going to happen to the amplitude whenever K is equal to M omega squared? The amplitude is going to be infinity. Okay, you're going to get a resonance, but a type of resonance that's going to destroy the whole system. That's going to make the mass flies away. Hopefully, we do have a damping there in the system that will not destroy our system. Okay, we're going to talk more about that next time. Any questions? So 157, I have office hours right now. If you want to talk to me, stay around, and I will see you tomorrow. Okay. Pause. I'm going to stop here.